All right, so I want to go ahead and start chapter 7 just with instead of going through the lecture, I want to go ahead and just talk about a set of problems and discuss them with you. And just maybe do a few examples, and then obviously I'll give you some work to do. Got it. What happened? No, it is new, but it's same thing with derivatives. It's just applications of it. So if you take a look at the questions here, like the first question says, for each of the following functions, f of x, find f of prime of x and the interval in which is increasing. And then in part 2, it says the interval which is decreasing. And I want to go ahead and I'm going to go and just copy these questions. And I'm going to open up the white book. And I'm going to go ahead and also discuss decreasing and discuss another part of it. So here we go. Let's get some notes in there. So here we go. Here we have the problem. And let's talk about this function here. So we have.
Hi.
Yes.
Do you have Sophia Cerruti?
I do.
Aren't you going home? Thank you.
Oh, okay.
Bye.
I already knew Sophia was leaving, so I'm acting like I'm disappointed. But I am sort of disappointed. I would have loved you to stay in the class. Did that sound like authentic?
No.
But I really was. I really do mean it. Like for real. Like I mean it. I want you to stay in the class. That sounded real though. She said, but it sounded real. It didn't sound like it was cynical. You think it was cynical? It felt real though. Okay.
Where do I put this?
In the fifth stack. When you count from left to right, from top to bottom.
Bye.
Take care, drive safely. All right, so here we have the function x squared minus 5x plus 6. Now, what shape is that? Why isn't it there? It's not on the board. Why? Oh man, always something. Come on, computer. Maybe it's just slow. Wait, I know what's happening. I know. Share this screen. Okay, watch. Now I'm gonna go here. Now we're good. So there we have what shape is that? What shape is x squared minus 5x plus 6? It is a parabola. Is this a face up or down? Up. Now, in this question, they're talking about when the f prime of x interval is increasing. Now, what I want to let you know is that a function is increasing when its derivative is positive. If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. And if the derivative is 0, it's stationary. So I'll go ahead and write that in symbology. If f prime of x is less than 0, we say the function is decreasing. If f prime of x is greater than 0, we say the function is increasing. If f prime of x equals to 0, we say the function is stationary at that point. Now, it's instructive for me to go ahead and do this, and not only that, and demonstrate using a graph so you can visually see it. So f prime of x, can somebody tell me what the derivative is? 2x minus 5. I'm so happy my Promethean board is working. It was not working for half the day. I don't understand why. But now it's working. I'm so happy. Did that sound authentic? Okay. So now I ask you, when is f prime of x here bigger than 0? When is it increasing? Well, when 2x minus 5 is greater than 0. So when x is greater than 5 half. So this function is increasing when x is greater than 5 half. She's not smiling at all. It's almost like she's perplexed.
Hi.
Did you see me at all?
Yeah, I did.
But you weren't like reacting in any way.
But I didn't know what I was supposed to react to your eyeball.
How is this supposed to happen? All right, so, and I'm recording this, darn it. Okay, so now, what if I want to find out when the function is decreasing? Well, in theory, f prime of x is decreasing, and in practice, of course, when the derivative is 0. And what's the derivative? The derivative is the slope of my tangent line. So then we just solve this same thing for when it's less than 0. So that'd be x is less than 5 half. So it's decreasing when f is less than 5 half. Agree or disagree? Now let's find out when it's stationary. Stationary. So when it's stationary, it's when f prime of x equals to 0. So 2x minus 5 equals 0 when x is equal to 5 half. And so right now with this one question, with 1a, we have discussed when functions are increasing, decreasing, or stationary. Yay or nay? Questions or concerns? Because now I'm gonna try to graph this. I think I should cheat and use the Desmos calculator, don't you think? Agree? It's better for us. But is everybody finished writing now? Now again, you know, there's some people in the class who are not doing anything. Where I've received emails from their parents asking for advice on what they should do. It's like, of course, you know, they were asleep half the class, you know. That's called being passive aggressive, right? Is that passive aggressive? No, what is passive aggressive? So how was I now? So how was I? All right, so now let's use Desmos calculator, but I see some people writing. I'm gonna give them no people stop writing. So I'm gonna go ahead and go to Desmos calculator. So here it goes, go into Desmos. Now, can somebody tell me the equation, what it was? What was the equation? Yeah, the original one. Give me 1 second. My tablet is not giving me a keyboard. There we go. What was it? Oops, wait, it has to be lowercase x. X raised to the second, what else? Minus, do you see my keyboard? Oh my gosh, there you go. Oh no, it has to be at the bottom. Minus, no, para acá. Minus 5x, right? What else? Plus 6. So if I did that, and I press enter here, I should zoom out and I should see it, and I don't see it because I wrote something wrong. That's what's wrong. Give me 1 second. Let me correct that. Keyboard. I'm gonna backspace that. There we go. Now it came out. So there is our graph. Now here's what I want you to notice. What's 5 half in decimal? 5 divided by 2, what decimal does it give you? 2.5. You see, that's here. Notice that when we go back to what we were doing, when x was greater than 5/2, it said it was increasing. Notice this curve here, how it's increasing over here. You see it? Like on this side here, it's increasing. The slope of your tangent line is positive to the right of 5/2. But over here, it's all negative slopes. You see that? All this is negative slopes. You see that? Let me go ahead and see if I can copy this image. Is there like a shortcut to copy? Like from here? Like, can I copy it? Like, give me 1 second. I'll figure it out. I think I can figure it out. Give me 1 second. How do I copy this image here? Control. Yeah, but I need to print screen. I need a print screen. How can I print screen from a touchpad? I don't know how to do it. But imagine I did. Imagine I did. Imagine I actually copied this and I put it here. And I also use the same ink. And it looks like this. And over here, what you notice is here's 5/2. Over here on this side, all my slopes on my tangent line are negative. And all over here, they're positive. You see? But right here, at the stationary, it's 0. And guess what? This is the minimum. It's the smallest point. It happens to be that everywhere we have a stationary point, we have a minimum or a maximum. Well, sometimes not. But we'll discuss that. What you want to see is that if the function from left to right is decreasing here and increasing here, we have a minimum. Sometimes a local minimum, because it might not be the real minimum of the function. It could just be a local minimum. You can imagine a situation where we have a parabola that looks like this, right? Where on the left here, it's increasing, it's positive. And then after it passes the stationary point, it begins decreasing, right? In that case, we would have a maximum. Agree or disagree? You see that? And so that's the whole point of this lesson. Can you figure out when a function is increasing or decreasing? Can you figure out where the stationary point is? And can you figure out if that stationary point is a maximum or a minimum? So just to kind of put the rules together, if f prime of x is greater than 0, it's increasing. If f prime of x is less than 0, it's decreasing. If f prime of x equals to 0, we have a stationary point. Now, sometimes these stationary points are not maximum or minimum, but we'll see. Because there's a possibility that you do have a stationary point where it doesn't go from positive to negative or negative to positive, but goes from positive to positive. And in this case, we call that an inflection point. So you could either have a maximum, a minimum, or an inflection. A maximum occurs when we transit positive to negative. So I think of it like this. I'm thinking positive, negative. Minimum looks like this, negative to positive. And an inflection, I think of it like this. A slurve. There's a positive, there's a stationary, and there's a positive. Or backwards. Negative. Maybe not so quite here, but yeah, you get what I mean. Yay or nay? Why are you guys so quiet? Why don't I feel joy from you? Sophia had joy in her face, even before she left class. Because you knew she was leaving. But I'm happy to be here. Do you think I'm happy to be here? So you think money is my motivation? You think I am a base individual who's motivated by money?
You started teaching because you're motivated by money.
Or despair?
Both, it doesn't matter. You were despairing because you had no money.
How about I was despairing because I had no purpose? How about that one?
Purpose in building pools. It's just the 2008 market crash. Like you needed that, you know. You can't lie to me.
These base thoughts. Ant-like thoughts.
You know.
All right, let's continue with the problems. So, where's my Adobe? I should have Adobe open. Adobe. Where is Adobe? Where is it? There it is, Adobe. All right, so now let's see, we have a challenging problem here somewhere, which is worthy of us. 5B, I don't want to do that one right now at this moment. At this moment, I don't want to do it, but maybe I want to do 4C. Is that fair? 4C? I want to do 4C. So I'm going to copy this and I'm going to go ahead and post it here. But what I'm going to do here is I'm going to analyze the full function as much as I can. So let's begin. How is this going to look, guys? It's to the third power. So it's like an S, like a slurve maybe. But let's see what it is. Okay. So we have y equals to x third minus 3x squared plus 3x minus 1. I'm going to go ahead and do the derivative of this. This is going to be 3x squared minus 6x plus 3. So the derivative is actually quadratic. The derivative is actually quadratic. Now, what I am going to do is I want to figure out when it equals to 0 first. So when is y prime equal to 0? 3x squared minus 6x plus 3 equals to 0. 3 times x squared minus 2x plus 1 equals to 0. So 3 times x minus 1 times x minus 1 equals to 0. So you can see that x equals 1 is what it's here, what's it all about. So there's only one, looks like there's only one stationary point. Now I like to make it like a little number line. Here's 1. And I'm gonna go ahead and just pick a number to the left of 1, let's say 0, and a number to the right one, let's say 2. And I'm gonna substitute that number, those numbers into my derivative. So y prime equals, let's go ahead and put 3 times 0 squared minus 6 times 0 plus 3. And so y prime equals to 0 minus 0 plus 3. You can tell it's going to be positive. So over here on this side, it's positive. It's increasing. Now I want to check what happens to the right of 1. So I'm going to go ahead and substitute 2 in there. So y prime equals to 3 times 2 squared minus 6 times 2 plus 3. So that's y prime equals 3 times 4 minus 12 plus 3. And once again, it looks like it's 3. It's just increasing again. So what's happening here is we don't have a maximum or a minimum. We have a transition point or an inflection point. So if I go back to the original function and I substitute like 1, so if I go y equals to 1 to the third minus 3 times 1 squared plus 3 times 1 minus 1, and it's 1 minus 3 plus 3 minus 1, and so y equals to essentially 0. Looks like it's 0. So when 1 comma 0 would be your point. So if I were to make a quick sketch of this, let me increase it. At 1 comma 0, and then I know 0 comma negative 1 is another point. It kind of like, maybe it does something like this. You know? That's what it looks like to me. And I know it's like there's a delay of like 5 seconds or more. Look at that. Well, it's better than nothing. So I want to see if I'm right because, you know, I could be wrong. So let's go ahead and graph this. I think it was x raised to the 3rd power minus what? What was it?
My bad. Well, no, the original one.
Yeah,
X to the third minus 2x squared.
minus 3x raised to the 2nd plus 3x minus 1. So you see, it is a slur. Okay. So we go back to my graph, although I should have been more aggressive in the way I drew it. But in general, let's go back to the graph. They were very aggressive what's happening here. And it's right, they're right, because in order for there to be 0 slope there should be something aggressive happening here. Okay. Now, let me show you something. I think it's interesting. So let's say I'm going to change something from this function. Let's just make it a little bit more interesting, or try to. I'm going to go back like this. There. I'm going to do this one. Now, you can say, Mister, you already saw how it looked. It doesn't matter if I saw how it looked. X to the 3rd minus 3x minus 1. So let me go ahead and write this on my board. X to the 3rd minus 3x minus 1. X to the 3rd minus 3x minus 1. We already saw the graph. But I want to show you that we didn't have to see the graph. If you take the derivative of this, you get 3x squared minus 3. And if you set that equal to 0 to find your stationary points, if you say y prime equals 0, we're going to have stationary points. Stationary. stationary points. You're gonna solve that. You're gonna solve that 3x squared minus 3 equals to 0. And that's pretty straightforward. It's 3x squared equals to 3. Divide by 3, that's 1. And so x equals plus or minus 1 because you're gonna square root. So now you have two potential answers for your stationary points. You have -1 and you have +1. Now, we're going to have now, as a consequence, 3 test points. Let's say you could pick -2, so you can pick 0, and say you can pick 2. So you're going to substitute that into your derivative to figure out if your function's increasing or decreasing at that respective value. So if you go to your derivative and you put 3 times -2 squared minus 3, you get 3 times 4 minus 3, which is 12 minus 3, which is 9. So this is positive. It's increasing here. So now we check what happens in the middle at 0. So we have 3 times 0 squared minus 3. So that's 0 minus 3, it's -3. So it's decreasing here. Decreasing. So now you see that it's going up here and then it goes down. So this has to be a maximum, a local maximum at the very least. Now we test that 2. So we have 3 times 2 squared minus 3. So 3 times 4 minus 3. So it's 12 minus 3. So that's 9. And now it increases. So now you know it goes back up. So now you know that here we have, and obviously that's a very bad drawing. And maybe I should isolate it differently. Maybe it should look something like this, where this will be a min here. So if you go back to the original graph and you take -1 to the third minus 3 times 1 minus 1. So we're talking about, we're here now. And we just want to get some points. You have that -1 minus plus 3 minus 1. So it's -1 plus 3 minus 1. That comes out to 1. So when it's -1, your point is 1, -1 comma 1. Right? And so we put 1 in there. We have 1 to the third minus 3 times 1 minus 1. So that's 1 minus 3 minus 1. And so you have -2 minus 1. So that's -3. So you have 1 comma -3. And so now let me make a brief sketch. So we have -1 comma 1. We have 1 comma -3. If we put 0 at 0, we have -1. And this one increases, then decreases, and then increases. So this is a local max, and this is a local min. And we made a sketch by using derivatives to analyze when the function increases and decreases. And by there, we can figure out if it's a maximum or minimum. Don't you think it's kind of neat that you could do this using derivatives? No, I think it's neat. You see? And they have the same thing I did. You see? And you can make a reasonable sketch without needing very precise numbers, just a few numbers, a little bit of analysis. Black Friday, net gear. So I think that's neat. Don't you think it's neat? So I think that's enough for today. What I will give you is I give you a set of problems. I love these problems right here. They're a lot harder than the ones I've gone over, but if you tackle them, you will feel like very smart. Make sense? Give me 1 second, just kind of closing everything out here. All right, so let me go ahead and stop the share. Let me go ahead and end this, and I have